Welcome to this walkthrough of LeetCode problem number 1516, Move Subtree of N-Ary Tree. In this problem, we'll explore how to restructure an N-Ary tree by moving a subtree rooted at a specific node to become a child of another node. Let's dive in and break this down step by step. In this problem, you are working with an N-Ary tree, which is a tree where each node can have multiple children. The tree is represented using a class called node, where each node has a value val and a list of its child nodes, children. You are given the root of the tree along with two integers, p and q. The task is to move the subtree rooted at node p so that it becomes a direct child of node q. However, there is an important constraint: if p is already a descendant of q, this operation is considered invalid. The tree is guaranteed to be valid, meaning that each node has a unique value, and there are no cycles within the structure. Your goal is to modify the tree according to these rules and ensure the operation is valid. To summarize, the task is to modify the tree structure by moving the subtree rooted at node p to become a direct child of node q, and then return the root of the modified tree. The input includes the root node of the tree, represented as a node object, and the integers p and q representing the values of the nodes involved in the operation. The output is the root of the modified tree, also represented as a node object. To understand this better, let's consider some examples that illustrate how the tree structure changes based on the inputs provided. In the first example, the input tree has a root node with value 1 and 3 children, 2, 3, and 4. Node 3 has a single child, 5. Here, p is 3 and q is 2, meaning we want to move the subtree rooted at node 3 to be a direct child of node 2. After the operation, the modified tree has node 3 as a child of node 2, and node 5 remains a child of node 3. The tree structure now reflects this change, with 2 having 3 as one of its children, alongside any other original children. This demonstrates a valid operation where the subtree is successfully moved. In the second example, the input tree is the same as before, but here p is 4 and q is 3. This means we want to move the subtree rooted at node 4 to become a direct child of node 3. After performing this operation, the modified tree shows node 4 as a child of node 3, alongside node 5. The rest of the tree structure remains unchanged, and the operation is valid, as 4 is not a descendant of 3, satisfying the problem's constraints. In the third example, the tree structure is the same as the previous examples, but this time p is 2 and q is 5. The task would involve moving the subtree rooted at node 2 to be a direct child of node 5. However, this operation is invalid because node 2 is an ancestor of node 5. Moving an ancestor to become a child of its descendant would create a cycle in the tree, which is explicitly prohibited. As a result, the tree remains unchanged, and the operation is deemed invalid. This highlights the importance of ensuring that the given operation respects the constraints. When solving this problem, it's essential to handle edge cases and constraints carefully. For example, in a minimal tree with only one node, where p and q refer to the same node, the tree remains unchanged. Similarly, if q is already a direct parent of p, the operation is invalid. For large trees with up to 1,000 nodes, the solution must be efficient while maintaining correctness. Finally, you must ensure that no cyclic references or invalid moves are introduced into the tree structure during the operation. These considerations are critical for implementing a robust and effective solution. To solve the problem of moving a subtree in an N-Ary tree, the first step is to consider the fundamental operation, reparenting the subtree rooted at node p to make it a direct child of node q. However, we must also account for constraints, such as ensuring that p is not already a descendant of q, since this would make the operation invalid. One approach we can consider is a brute force method that involves directly traversing the tree. In this approach, we would locate nodes p and q, validate that p is not a descendant of q, and then modify the tree structure by removing p from its current parent and attaching it to q. While this method is conceptually straightforward, it involves multiple tree traversals, first to locate the nodes, then to validate the constraints, and finally to perform the updates. This leads to a time complexity of O(n) squared, in the worst case, which is inefficient for large trees. Moreover, the redundant traversals make it less scalable. A more optimized approach leverages a parent mapping to achieve the same outcome with greater efficiency. By creating a mapping of each node to its parent during an initial traversal, we can significantly reduce the time spent locating nodes and validating relationships. Using this parent map, we can efficiently check whether P is a descendant of Q by traversing upward from Q. If the validation passes, we can then adjust the pointers directly to remove P from its current parent and attach it to Q. This reduces the overall time complexity to O(n), as building the parent map takes O(n), validation is O(h), based on tree height, and the pointer adjustments are constant time. However, this approach does require additional memory to store the parent map, which has a space complexity of O(n). An alternative to this would be a recursive approach that combines validation and modification into a single function. While this reduces the need for additional memory, it introduces the risk of stack overflow for deep trees and can be more complex to implement. The chosen strategy is the optimized approach that uses a parent map, as it strikes the right balance between clarity, efficiency, and robustness. One of the key insights here is that maintaining a parent-child relationship explicitly through a parent map allows us to perform both validation and updates in linear time. This is particularly important for verifying that P is not a descendant of Q, which can be efficiently done by traversing upward from Q using the parent map. Additionally, this structured approach ensures that pointer manipulation is handled carefully, preserving the integrity of the tree. Compared to the brute force method, this approach eliminates redundant traversals, reducing time complexity from O(n)² to O(n). While it does introduce an O(n) space overhead for the parent map, this trade-off is acceptable given the significant performance gains. It is also more robust than the recursive approach, as it avoids stack overflow risks and handles edge cases like P being a descendant of Q or invalid inputs gracefully. In conclusion, the optimized approach provides a clean, efficient, and scalable solution to the problem. By separating the tasks of building the parent map, validating relationships, and updating pointers, this method ensures clarity and maintainability. The trade-offs, such as additional memory usage, are minimal compared to the benefits of reduced time complexity and improved robustness. Overall, this approach allows us to handle edge cases effectively, avoid unnecessary computations, and maintain the integrity of the tree structure, making it the best choice among the alternatives considered. To solve the problem of moving the subtree rooted at node P to become a direct child of node Q in an N-Ary tree, we need a clear approach. First, it's important to understand the input structure. The tree is composed of nodes where each node has a list of children. The task requires modifying this structure by relocating the subtree rooted at P. However, there are some constraints to consider. For example, if P is an ancestor of Q, moving P under Q would create a cycle, which is not allowed. Similarly, if P is already a child of Q, no changes are necessary. Additionally, we must ensure that both P and Q exist in the tree, otherwise, the operation is invalid. To handle these steps, we start by traversing the tree using either depth-first search, DFS, or breadth-first search, BFS. During traversal, we keep track of each node's parent, which will help in removing P from its current parent and checking for ancestor relationships between P and Q. Once the parent mapping is built, the next step is to verify if P is an ancestor of Q. This is done by tracing back from Q to the root using the parent map. If P is encountered at any point during this trace, the operation is invalid because moving P under Q would create a cyclic structure in the tree. After confirming the validity of the operation, we proceed to modify the tree structure. First, we remove P from its current parent's list of children. Then, we append P to the children of Q, effectively relocating the subtree. It's important to ensure that the tree structure is updated correctly throughout this process. Some key takeaways include the importance of the ancestor check in maintaining the tree's integrity, the efficiency of using a parent mapping for traversal and validation, and the necessity of handling edge cases such as invalid nodes or no-op scenarios. The tree is typically represented using a tree node class, which includes a value and a list of children, and the parent map is implemented as a dictionary to simplify operations. Analyzing the computational complexity of the algorithm, we see that the time complexity is O(n), where n is the number of nodes in the tree. This is because we traverse the entire tree once to build the parent map and perform ancestor checks. The space complexity is also O(n), as we store the parent mapping for all nodes. Let's look at the pseudocode for the algorithm. First, we define the function moveSubtree, which takes the root of the tree, node P, and node Q as inputs. We initialize an empty parent map and define a helper function to perform a DFS traversal. During the traversal, each node is mapped to its parent. Once the parent map is built, we check if either P or Q is missing from the map. If so, the operation is invalid, and we simply return the root. Next, we check if P is an ancestor of Q by tracing back from Q to the root using the parent map. If P is encountered, we return the root without making any changes, as the operation would create a cycle. After handling invalid cases and ensuring that P is not an ancestor of Q, we proceed to modify the tree structure. Using the parent map, we identify P as current parent. If P has a parent, we remove P from its parent's list of children. This effectively detaches the subtree rooted at P from its original position. Then, we append P to the list of children of Q, making Q the new parent of P. Finally, we return the updated root of the tree. Key operations in this process include the use of the parent map, which simplifies both the removal of P from its current parent and the ancestor checks. The ancestor check is crucial for preventing cycles, ensuring the tree's structural integrity. The tree modification steps are carefully designed to preserve all relationships within the tree, except for the specific changes required by the problem. For deeper trees, BFS can be used instead of DFS to prevent stack overflow, providing a more robust solution for large inputs. To optimize the algorithm further, we can avoid redundant ancestor checks by marking nodes as visited during the traversal. This ensures that we don't repeat unnecessary operations, improving efficiency. By keeping track of visited nodes, we streamline the process of validating the tree structure and performing modifications. This small but effective improvement reduces the computational overhead and ensures that the algorithm runs smoothly even for larger and more complex trees. Here, we start with the definition of the node class, which represents a single node in our N-Ary tree. Each node has a value, stored in val, and a list of children. If no children are provided during initialization, it defaults to an empty list. Moving on to the solution class, the primary function moveSubtree is defined to handle the process of moving a subtree from one node to another. A helper function, findParentNode, is introduced to locate both the target node and its parent in the tree. This function works recursively, traversing the children of each node until it finds the target. If the target is found, it returns the parent and the node itself, otherwise, it returns none. Using this helper, we then locate the parents and nodes for both P and Q, the nodes involved in the move. Next, we handle the special case where Q is already a child of P. In this scenario, Q is temporarily detached from P to prevent a circular reference. If P has a parent, it is prepared for removal from its current position. Now, if P has a parent, it is removed from its parent's list of children. Then, Q becomes the new parent of P by appending P to its list of children. This completes the special case handling where Q was originally part of P's subtree. For the general case, where Q is not a child of P, the process is straightforward. First, if P has a parent, it is detached from its current parent. Then, P is directly added as a child of Q by appending it to Q's list of children. This ensures that P is successfully moved under Q, regardless of their initial positions in the tree. Finally, the function returns the modified root of the tree, so the caller can work with the updated structure. This implementation ensures that the move operation is handled cleanly and efficiently for all possible scenarios. Here, we start by defining the node class, which is the fundamental building block of our N-Ary tree. Each node has an integer value, val, and a list of children nodes. We provide three constructors, a default constructor initializing an empty list of children, one that initializes the node with a value, and another that takes both a value and a predefined list of children. Moving on to the solution class, we define the main method, moveSubtree, which will handle the logic for moving a subtree from one node to another. To achieve this, we first use a helper method, findParentNode, which will locate the parent and the target node we want to manipulate. This helper returns an array containing the parent and the node itself. We begin by calling this method to find the parent and the node for the first target, P. Next, we use the helper method again to locate the parent and the node for the second target, Q. Once we have both sets of parent and node references, we evaluate the relationship between P and Q. If Q is already a child of P, we temporarily remove Q from P's children. Then, if P has a parent, we detach P from this parent to prevent cyclic references. After these adjustments, we add P as a child of Q. On the other hand, if P and Q are unrelated, we handle the general case. Here, we detach P from its parent, if it has one, and add P directly as a child of Q. Finally, we return the modified tree's root, ensuring that all changes are reflected in the original structure. To support these operations, the find parent and node helper method traverses the tree recursively. Starting from the root, it checks if the current node matches the target. If it does, it returns the parent and the node as an array. Otherwise, it iterates through the children of the current node, performing recursive calls to explore deeper levels of the tree. If the target is found at any point, the helper returns the parent-child pair. If the traversal completes without finding the target, the method returns null for both parent and node. This helper is crucial for isolating the nodes we need to manipulate while preserving the structure of the tree. In this example, we are tasked with moving a subtree in a general case scenario. The input tree has node 1 as the root, with children nodes 2, 3, and 4. Node 2 itself has children nodes 5 and 6. Here, we want to move the subtree rooted at node 2 to become a child of node 4. To achieve this, we start by initializing our key variables. The root is node 1, while node 2 is our subtree to move, labeled as P, and node 4 is the destination, labeled as Q. The first step is to locate the parent of node 2. This is straightforward as node 2 is directly a child of node 1, making node 1 the parent of P. Once we identify the parent of node 2, which is node 1, we confirm that node 2 itself is the subtree we want to move. Next, we find the parent of node 4, which is also node 1, since node 4 is another direct child of the root. With both parent nodes identified, the next step is to detach node 2 from its current parent. This means we remove node 2 from the children list of node 1. The children of node 1 now consist of nodes 3 and 4. After detaching, we attach node 2 as a child of node 4 by appending it to node 4's children list. The tree structure is updated accordingly, with node 4 now having node 2 as its child. The final tree reflects this change. Node 1 has nodes 3 and 4 as its children, and node 4 now has node 2, which still retains its original children, nodes 5 and 6. In this second example, we are dealing with a special case where the destination node, Q, is already within the subtree rooted at P. The input tree has node 1 as the root, with two children, node 2 and node 3. Node 3 further has node 4 as its child. Here, P is node 2, the subtree we want to move, and Q is node 4, the destination. We start by initializing our variables. The root remains node 1, while node 2 is identified as P and node 4 as Q. The first step involves finding the parent of node 2, which is node 1, given node 2 is a direct child of the root. Next, we locate the parent of node 4, which is node 3 since node 4 is a child of node 3. Before we can move node 2, we first need to detach node 4 temporarily from node 2's subtree. This is done by removing node 4 from node 2's children list if it exists there. Then, we detach node 2 from its parent, node 1, by removing it from node 1's children list. Node 1's children now only include node 3. Finally, we attach node 2 as a child of node 4 by appending it to node 4's children list. The updated tree structure shows node 1 with nodes 3 and 4 as its children. Node 4 now has node 2 as a child, completing the move. This example explores the scenario where P and Q are siblings. The input tree has node 1 as the root, with 3 children, nodes 2, 3, and 4. In this case, node 2 is identified as P, the subtree to move, and node 3 is Q, the destination. The first step is to locate the parents of both node 2 and node 3. Since both are direct children of node 1, their parent is node 1. Once the parent nodes are identified, we move to detach node 2 from its current parent. This is done by removing node 2 from node 1's children list. The updated children of node 1 are now nodes 3 and 4. With node 2 detached, the next step is to attach it as a child of node 3. This is achieved by appending node 2 to node 3's children list. The final tree reflects this change. Node 1 now has nodes 3 and 4 as its children, but node 3 itself has node 2 as its child. This completes the process of moving the subtree, with the tree now showcasing the modified hierarchy where node 2 is successfully nested under node 3. To analyze the time complexity of our solution, let's break it into two key parts. First, the find parent and node function performs a recursive traversal of the N-Ary tree. In the worst-case scenario, it visits every node in the tree, which means its complexity is proportional to the number of nodes, n. Since we call this function twice, once for p and once for q, the combined overhead is O(n), which simplifies to O(n). Next, we consider the tree modification step. Removing a node from its parent's children list requires a linear search and removal, which takes k time, where k is the number of children of the parent node. Adding the node to another children list is an O(1) operation for appending at the end. Therefore, the dominant factor in tree modification is the linear search, which is bounded by the branching factor, b. This step takes b time in the worst case. Now, let's consider the overall time complexity. Since the recursive traversal dominates the process and is O(n), the contributions from tree modifications, which are O(b), are negligible for large n. This gives us an overall time complexity of O(n). Moving on to space complexity, the main consideration is the recursive call stack used by find parent and node. The maximum depth of recursion is equal to the height of the tree, denoted as h. In the worst case, such as in a degenerate tree, the height could be as large as n, resulting in a space complexity of O(n). For a balanced tree, however, the height is proportional to log n, so the space complexity in this case would be O log n. Additionally, the algorithm does not require any extra data structures, so the auxiliary space remains constant at O(1). To summarize the overall space complexity, in the worst case, it is dominated by the recursion stack, leading to O(n). However, in a balanced tree, this is reduced to O log n. Now, let's compare this with a brute force approach. A naive method might involve completely reconstructing the tree after moving the subtree. This would require traversing the entire tree, resulting in a time complexity of O(n). However, it would also demand additional space to create a new tree structure, leading to an auxiliary space complexity of O(n). In contrast, the optimized approach modifies the tree in place. This eliminates the need for extra memory, keeping the auxiliary space at O(1). The time complexity remains O(n), since it is primarily determined by the traversal step. Let's wrap up with a best, average, and worst case analysis. In the best case scenario, if p and q are located at the root or very close to it, the traversal depth is minimal, and the time complexity approaches O(1). On average, the algorithm traverses a portion of the tree to locate both nodes, resulting in a time complexity of O(n). In the worst case, such as in unbalanced or degenerate trees, the algorithm may need to traverse the entire tree, leading to O(n) time complexity. Mathematically, this is consistent with big O analysis. The recursive traversal of the N-Ary tree visits each node exactly once, contributing O(n) operations. Modifications, such as removing or adding nodes, involve operations dependent on the number of children, b, which is negligible compared to n. Finally, the recursion stack depth is bounded by the tree height, so the space complexity is O(h). In the worst case, this is O(n), but for balanced trees, it reduces to O log n. Overall, the solution achieves O(n) time and O(n) space in the worst case, with significant optimizations over naive approaches due to in-place modifications. When working on this problem, there are several common mistakes developers might encounter. First, forgetting to handle the edge case where p is already a descendant of q can be problematic. If you move p under q without checking, it creates a cycle in the tree, which violates the fundamental property of a tree. This can be avoided by using a traversal, such as DFS, to confirm whether q lies in the subtree rooted at p before making any changes. Next, it's essential to properly disconnect p from its original parent. If this step is incomplete, the original parent may still treat p as a child, leading to a corrupted tree structure. To fix this, ensure you explicitly identify p as parent and remove p from its child list. Lastly, mismanaging the order of operations is another common issue. If you modify the tree structure before verifying all preconditions, you risk creating invalid states or leaving the tree partially updated if an error occurs. To address this, always validate constraints such as checking that P is not a descendant of Q and confirming the existence of P and Q before making any modifications to the tree. Another common variation to be mindful of involves handling root nodes. If P is the root of the tree, it requires special handling since it doesn't have a parent. You need to include logic to check whether P is the root and appropriately update the root reference when moving it. Additionally, inefficient traversal is a frequent pitfall, particularly with large trees. Using multiple redundant traversals to locate P and Q can lead to suboptimal performance. Instead, you can optimize by using a single traversal to find both nodes or by pre-computing parent references in a hash map. This allows for O1 lookups, significantly improving efficiency. Understanding key insights about trees is crucial for success in this problem, especially in an interview setting. A tree is an acyclic connected graph, and any modification must preserve this property. For instance, moving P under Q can accidentally introduce a cycle if Q is already part of the subtree rooted at P, so you need to explain how you detect and prevent this. Efficiency is another critical factor. Interviewers often expect solutions with O(n) complexity, where n is the number of nodes in the tree. Avoiding unnecessary traversals can help achieve this. It's also important to discuss edge cases thoroughly, such as scenarios where P is the root or when P or Q doesn't exist in the tree. Lastly, clear communication is key. Walk interviewers through your approach step by step, using diagrams to demonstrate how the tree is modified, if necessary. This problem shares similarities with several related LeetCode problems, which can help you deepen your understanding of tree manipulation. For example, LeetCode 1506, which involves finding the root of an N-Ary tree, focuses on tree traversal and understanding parent-child relationships. LeetCode 1485, which deals with cloning a binary tree with random pointers, emphasizes maintaining structural integrity while handling edges. Another related problem, LeetCode 1376, involves calculating the time needed to inform all employees in an organizational hierarchy, a tree-based problem that highlights traversal and parent-child dynamics. Finally, LeetCode 428, which focuses on serializing and deserializing N-Ary trees, requires careful handling of parent-child connections during reconstruction. Familiarizing yourself with these problems can provide valuable insights and techniques for solving tree-related challenges. There are alternative approaches to consider when solving this problem, each with its own trade-offs. One option is to use a depth-first search with post-processing. In this approach, you first locate P and Q using DFS, then perform the move after verifying all constraints. This method is straightforward to implement but may involve multiple traversals. Another approach is to use a hash map to store parent references during the traversal. This allows for O1 lookups when disconnecting and reconnecting nodes, which can reduce redundancy and improve efficiency. However, it does require additional space. Finally, you could use an iterative traversal, such as a stack or queue, to locate P and Q. While this method saves recursion stack space, it may be less intuitive to implement compared to DFS. Choosing the right approach depends on the problem constraints and your familiarity with these techniques. Great job following along. To summarize, we tackled the move subtree of N-Ary tree problem by focusing on tree traversal and node restructuring. This is an excellent problem for honing your tree manipulation skills. Thank you for watching, and I hope to see you in the next problem walkthrough. Happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!